So module 2, vector spaces. In this module, these are the main topics. First topic is what is a vector space and problems. Show that the given set is a vector space using these operations like that. Second one, dimension, basis and dimension. This is the subset of a vector space which is linearly independent. There is some dimensions, basis and dimension. Later, problems. So based on the definitions, find the basis and dimension of the vector space. Next topic, linear combination and span. Linear combination and span. So what is a linear space? So linear combination. Linear combination means just like sum with scalar multiples of the vectors. The resultant set is a vector space or not, like that. This is the a part of the vector spaces. Every topic has a problem. So what is a vector space definition, as well as based on the definition we have a problem. So now today I am going to discuss about vector space. What is a vector space? So vector space, also named as linear space, this contains two sets. One of the set is field. In your BSc level, you already learn about groups, rings, fields. Field is a nothing but a set with two operations, addition and multiplication. With respect to addition, it is an abelian group. With respect to multiplication, the non-zero elements form a group, abelian group, and distributive properties. Here also same thing. And V is the set, contains the elements. V is one set, F is a field. This V is called a vector space if it satisfies the following operations. V is a vector space or over F if V satisfies the following operations. V with respect to addition is abelian group. A alpha plus beta belongs to V for every alpha comma beta belongs to V. This is called closure property. Alpha plus beta equal to beta plus alpha, commutative, associative property, identity, inverse. Then after finishing abelian group properties, this is a scalar multiplication. Scalar multiplication means field to vector place. F cross V to V. Take a scalar. Usually scalars is denoted by C, A, B, C. So C into some vector. The resultant one is a vector W, like this mapping. So this is the fourth property, indicate the scalar property. This is called scalar property. So a rule or operation called scalar multiplication, which associated with each scalar C in F, and first you take scalar and a vector alpha. A vector, the resultant one, C cross V is denoted by C. In place of V, they use alpha. C alpha in V. This value nothing but W, resultant value. C alpha, nothing but image value in V, called the product of C and V, in such a way that, so this operation or this mapping satisfies the following operation. 1 into alpha equal to alpha. That means you take 1 in the field, V in vector space, the resultant mapping element is V. Similarly, C1, C2 of alpha equal to C1 times of C2 of alpha. C of alpha plus beta equal to C alpha plus C of beta. C1 plus C2 of alpha equal to C1 alpha plus C2 of alpha. These four properties with respect to scalar multiplication. V is abelian group and scalar multiplication satisfies these four properties. Then it is called a vector space over the field F. Okay. Next, here I provide the 5 problems. First problem is let F be any field. It may be real field, real number field, or rational number field, or complex field, or binary field, whatever it may be. And let V be the set of all n tuples. Show that V is a vector space over the field with respect to the following operation. So the sum of the vectors is defined like that, component wise addition. Alpha plus beta equal to, here I'm missing the word, alpha plus beta equal to component wise addition. It means adding all first component, second component, third component, like that. So first component means x1 plus x2. Here, as usual, now x1 first component plus first component of the second vector. Here first component is y1. This is the first component of the resultant vector. Then second component of the first vector x2. Then second component of the second vector. This is the operation they are given. Already they are given. So using these operations, we want to show that it is a vector space and so on. The last vector is last component and last component, xn plus yn. This is the operation they are provided. Scalar multiplication also defined component wise. So C alpha, alpha is a n-tuple vector, x1, x2 already we taken in the first one, x1, x2, x3, xn. C times of alpha means C of x1, x2 and so on xn. Now C move to inside of each component, C alpha 1, C alpha 2, C alpha n and so on. This is the first problem. Now I am going to prove this as a vector space with respect to these two operations. Okay. Proof. Okay. Proof of the problem. Usually answer, because it is a problem, usually we say that answer. If it is a theorem, we say that it is a proof. Okay, answer to this problem. So in examination point of view, you write down what are the given hypotheses. Let F be any field and V be a n-tuple vector space. It means you understand that given that F is any field and the set V equal to, also given that the set V equal to n-tuple x1, x2 and so on xn, such that these n-tuples of components taken from field, each xi 1 less than or equal to I less than or equal to n, taken from field F. This is element from field, this is element from field and so on, all possible elements. This is the V. All defined alpha plus beta, alpha, let alpha equal to x1, x2 and so on xn, beta equal to y1, y2 and so on yn, and C belongs to, these two are belongs to vectors V, set V, and C is a arbitrary constant which belongs to F. Now first thing is to show that, actually our goal is to show that V is a vector space over the field F. So for this purpose, we want to show that V plus is a abelian group. Already plus is given. How to operate two vectors with the plus sign. Already they are given. Usual addition. Usual means component wise. So closure property. Abelian group means closure property, closure axiom. So closure axiom. In closure axiom, we take two vectors. Let alpha x1, x2, and so on, xn, and beta y1, y2. These two are any two arbitrary vectors in V. To show that their sum, now by the hypothesis alpha plus beta equal to x1 plus y1. I'm not writing all the things. X2 plus y2 and so on, xn plus y1. Since by the hypothesis. Okay, since by the hypothesis. So this is nothing but component wise. X1 and y1 are elements in the field. Therefore, their sum is also belongs to field. So this is element of field, this is element of field, this is element of field. So every component is taken from the field. Therefore, it is a element in the V. So closure over. Next, associative property. Associative property or associative axiom. Sometimes I am written property, sometimes I am mentioning axiom. Both are same. But uniformly you assigned from the starting onwards. In the first axiom I mention first property I mention axiom. So it is better to mention axiom. So associative axiom. So now take three vectors alpha, beta, and gamma belongs to V. Alpha, x1, x2, we don't know component. So it is arbitrary vector. Say x1, x2, and so on, xn. Similarly, beta also we don't know. Say y1, y2, and so on, yn. And gamma, w1, w2, and so on, wn. So now we want to show that alpha plus beta plus gamma. First evaluate this. First, within the braces, we need to evaluate. So x1 plus y1, x2 plus y2, and so on, xn plus yn. This is a braces value. Write down gamma as it is. W1, W2, and so on, Wn. Now what happened? Now once again using the properties of vector additions by the first property of the hypothesis, addition of the vectors, because this is in V. Already by using closure property, this is in V. Now using the property of vector addition in V, x1, y1 plus w1, x2, y2 plus w2, and so on, xn, yn plus wn. All are elements in field. So once again, it is an element of V. So now our intention is, so these are the elements in the field. Field satisfies the associative property. Now you consider these two as a last two as a one part. This is vectors are written in the form x1, x2, and so on, xn plus y1 plus w1, y2 plus w2 plus and so on, yn plus wn. Now, which is equal to, this is nothing but alpha. Here we have two vectors. So once again, apply the same property. W1, comma, W2, and so on, Wn plus, sorry, Y1, comma, Y2, comma, and so on, Yn. This is the first vector plus W1, comma, W2, comma, and so on, Wn. This is second vector. So the name of the first vector in the braces is beta. Second vector is gamma. So associative property over. Then identity axiom. Identity axiom. Zero vector contains all entries are zero because field has a additive identity. This is a vector in V because each entry nothing but additive identity of field. And take any alpha. x1, x2, xn. Then what about 0 plus alpha? 0 plus alpha nothing but 0 plus x1, 0 plus x2, and so on, 0 plus xn. 0 plus any element equal to same element by the property of field. Inside element have the properties of field. So once again we get the alpha. Similarly, alpha plus similarly alpha plus 0 equal to alpha. It means there exists a vector such that alpha plus 0 equal to 0 plus alpha equal to alpha for every alpha belongs to V. So hence identity property over, identity axiom over. Then inverse axiom. Inverse means alpha is said to be inverse of beta if their sum equal to identity. Identity here, identity value is O. O is n tuples of zeros. So let alpha belongs to V. Therefore, minus alpha. Minus alpha becomes alpha is x1, x2, where alpha equal to n tuple x1, x2, and so on, xn. Therefore, minus alpha equal to minus x1, minus x2, and so on, minus xn. Component wise minus 1, because second property of the hypothesis, scalar multiplication, using scalar multiplication. C alpha equal to Cx1, Cx2. Here C value is minus 1. This is also belongs to field, because x1 in the field, minus x1 is also field. Each component is in the field. Now, alpha plus of minus alpha. This resultant value equal to component wise addition. x1 plus of minus x1, x2 plus of minus x2, plus and so on, xn plus of minus xn, which is equal to 0, 0, 0, and so on, 0. So it is a additive identity in the vector space. This value nothing but additive identity in the vector space. Therefore, inverse also exists. Therefore, or thus, for any vector v, for any vector alpha in V, there exists minus alpha in V such that alpha plus of minus alpha is same as minus alpha plus alpha equal to identity. Inverse over. Commutative axiom is simple. Commutative axiom. Commutative axiom or abelian axiom. Commutative axiom means take two vectors, let alpha comma beta belongs to V. I am taking alpha beta as usual previous values only. Now alpha plus beta equal to x1, x2, and so on, xn. Alpha value, beta value is y1, y2, and so on, yn. By the hypothesis, it is component wise addition. x1, y1, x2, y2, plus and so on, xn, yn. Now, the elements in the components are the elements of the field. Therefore, in the field, we have a commutative property with respect to addition. So, interchange the order of the elements in the component wise because of field property. Now, this is written by using property. This is written as y1, y2, and so on, yn, plus x1, x2, and so on, xn. First one, nothing but vector beta. Second one, nothing but vector alpha. So, it satisfies the commutative. First part over. Next, scalar multiplication property. scalar multiplication axioms. Now observe that let already they have given C times of alpha equal to vector. Start with the first property. In scalar multiplication property, first one is 1 times of, as your wish, there are 4 properties, one by one we will prove. 1 into alpha. We want to evaluate this. We want to show that this value equal to alpha. 1 into alpha. 1 into alpha means vector x1, x2, and so on, xn. 1 is a scalar. In place of c, we have 1. As per hypothesis, this value nothing but 1 into x1, 1 into x2, send 1 inside, 1 into xn. 1 into x1 nothing but x1, because x1, 1 is a multiplicative identity in the field. So xn. This is once again nothing but alpha. So one of the property of the scalar multiplication over. Second property. C times of alpha plus beta. We want to show that C alpha plus C beta. Okay. Now start with C alpha plus C beta. If you forgot, you remember the definitions. So in the definition, you see the properties of the scalar 1 into alpha. Next property C1, C2 alpha. Next property C of alpha plus beta. Next property C1 plus C2 plus alpha. In any order you can prove, but we require 4 conditions. C times of alpha plus beta value I am writing directly. In the examination point of view, don't write directly. Xn plus Yn, which is equal to, by the hypothesis, this value is C times of x1 plus x2, sorry, y1, C times of x1 plus y1. Second one is C times of x2 plus y2, and so on, C times of xn plus yn. Now, this value nothing but C x1 plus C y1, C x2 plus C y2, plus and so on, C xn plus C yn. Okay. Now, once again using property, it is written as Cx1, Cx2, this is x2. Then and so on, Cxn, first vector, second vector, Cy1, Cy2, and so on, Cyn. So now take a C as a common, because using property, their hypothesis, operation hypothesis, take C as a common. By the hypothesis, C as a common. So this is nothing but C alpha plus C beta, because this value nothing but alpha, this value nothing but beta. Now, second property over. Next, third property. Third property. C1 plus C2 times of alpha. C1 plus C2 times of alpha value is x1, x2, and so on, xn. Scalar plus scalar is scalar. If you think this is a C, enter into inside C1 plus C2. It means C times of x1, C times of x2, and so on, C times of xn. Just you think this is a C. If you have C times of x1, C times of x2. And so on, C times of xn. Okay. Now replace C value. Now in the scalar and vectors, C1 plus C2 of x1 nothing but C1 x1, C1 x1 plus C2 x2. Okay. C1 x1 plus C2 x1, comma C1 x2 plus C2 x2, and so on. C1 xn plus C2 xn. Now it is written as C1 x1, C1 x2, and so on. All C1 terms taken in one vector, all C2 coefficient terms in the taken in another vector. C2 xn. Now in the first one, C1 is a common, x1, x2, and so on, xn. In the second one, C2 is a common, x1, x2, and so on, xn, which is equal to C1, this is nothing but alpha, plus C2, this is nothing but alpha. So yeah, RHS over. Last property, C1 times of C2 alpha, C1. C2 sent to inside of vectors. Then the resultant vector becomes C2 x1, C2 x2, C2 x3, and so on, C2 xn. Now, once again, it is a vector, it is a scalar. Using the second hypothesis of the operation, send inside C1, C2, x1, C1, C2, x2, C1, C2, x3, and so on, C1, C2, xn. Now, C1, C2 is a scalar like Cx1, Cx2, Cx3. So, take C is a common out. C1, C2 times of x1, x2, x3, and so on, xn. This is nothing but alpha. C1, C2 times of alpha. Therefore, all properties are obeys the sets V and F. Therefore, V is a vector space over field F. That's all. First problem over. Similarly, we see the second problem. Matrices, M by N matrices. Same order, M and N values, suppose 2 by 3. You consider all 2 by 3 matrices, or 4 by 5. You consider 4 by 5 or 4 by 4, as your wish. You take same type of models, same order matrices. Okay. This is the second problem. Let F be a field, any field, and V be the set of all M by N matrices over the field, so that V is a vector space over the field with respect to the following operation. Here we always provide the vector addition, scalar multiplication. Using these two operations only, we need to prove that. Okay, with respect to vector addition. Vector addition is row wise. First row, second row, third row, third row. IJ means row value, column value indications. Here also, C times of Aij means ith row, jth column. It is multiplied with C. Every row is multiplied with C. Every entry of the, simply you remember that every entry of the matrix multiply with C. Using these two operations, show that V is a vector space. Okay, answer. So F is any field. Here V is a set of M by N matrix. Okay, A is M by N matrix. The entries of matrices usually denoted by small aij. Aij are taken from field. I value is row indication. Here row value up to n, m, 1 less than or equal to I less than or equal to m. J value indicate the column. So this value maximum n. Each entry of the matrix is taken from field F. This is V. So to show that V is a vector space over the field F. So V plus is abelian. First part is to show that two parts with respect to vector addition, with respect to scalar multiplication. Addition of two matrices, everyone knows. Just briefly, I am explaining closure property, closure axiom. So A plus B, usually A is in the form A11, A12, for example, A1n, A21, A22, and so on, A2n, and so on. Last vector AM1, AM2, AMN. This is one of the vector in our set V. Similarly, B11, B12, and so on, B1n, B21, B22, and so on, B2n, and so on, BM1, BM2, and so on, BM2. So usual vector addition, I mean matrix addition, component wise. First component A11, first component of the second matrix B11. This is the resultant first component A12 plus B12, and so on, A1n plus B1n. This is the first row of the resultant vector. Similarly, A21 plus B2, B2, A22 plus B22, and so on, A2n plus B2n, and so on. Last, AM1 plus BM1, AM1 plus BM1, AM2 plus BM2, and so on, AMN plus BMN. So once again observe that sum of field elements is also a field element. So it is a m by n matrix. Each entry belongs to field. So it belongs to our set V. Closure axiom over. Similarly, associative identity inverse zero matrix is the identity. Inverse means taking minus, do it yourself. Closure, associative. Next property is associative axiom. We know that. We know that matrix multiplication satisfies the associative property. Based on the time you can prove it. Matrix addition. Here our operation is addition. Matrix addition satisfies the associative axiom with respect to addition. Our matrices satisfies the associative axiom with respect to addition. You write down like that, the sentence formation. So therefore, alpha, beta plus, A plus B plus C equal to A plus B plus C for every, in our set also we have a matrices. So in V also satisfies the associative property, because matrices satisfies the associative property. See, V contains the matrices, therefore our V also satisfies the associative property. So identity axiom. Identity axiom. Zero matrix exists. There exists zero, everyone knows. Zero is also a matrix. Zero M by N matrix. There exists zero M by N matrix in V such that 0 plus 0 matrix plus any matrix in V, A plus 0 equal to A for all A matrix belongs to V. Identity over. Next, inverse. Inverse axiom. So matrix inverse. So just with respect to addition, taken with negative sign. So minus A. If A belongs to V, then because it is M by N matrix. Minus A also M by N matrix whose entries belongs to field. So it is also then is also belongs to V. And A plus of minus A equal to 0 matrix. Therefore, inverse is also exist. That means thus for any A belongs to V, there exists minus A belongs to V such that A plus of minus A equal to 0. Inverse over. Then abelian. Abelian X. Obviously true. Matrix multiplication satisfies the A plus B equal to B plus A. With respect to addition, okay. Multiplication only problem. Okay. We know that the matrix multiplication always going to operation multiplication. Matrix addition satisfies the commutative property. Satisfies the commutative property. Commutative. Therefore, in V also we have a matrices. So it satisfies the A plus B equal to B plus A for all A comma B belongs to V. So next scalar operations, scalar multiplication operations. So first property 1 into matrix A. Already you know in elementary class A equal to 1, 2, 3, 4. 3A means multiply each component with 3 times. 3 into 1, 3 into 2, 3 into 3, 3 into 4. Here also same thing. So 1 into A equal to 1 Aij. It is M by N matrix. Usually matrix A is denoted by A is a M by N. Now here also component wise multiplication. 1 into any scalar equal to same scalar. A is the element of the field, so it is called scalar. So 1 into any value equal to same value. This is nothing but A matrix. First property over. Now second property. C times of A plus B, which is equal to C times of two matrix additions. Matrix addition is nothing but component wise addition of the entries. A is a, B is a. A is a, B is a. Now send C inside. C times of A is a plus B is a M by N. C A is a plus it is written in the form C times of A plus B by using distributive property of the scalar. C A is a, C B A is a M by N. Once again using matrix addition property, it is written in the form C A is a C A is a M by N plus C B A is a M by N. Okay. Now, which is equal to C is common out. C A is a M by N plus C B A is a M by N. So this is nothing but a C A plus C B. That's all. Second property over. Next, third property. C1 C2 times of A equal to C1. C2 times of A becomes send C2 inside. I'm writing directly. C2A is A. Now, this is matrix, this is constant by the second axiom or second hypothesis of the theorem, scalar multiplication. Send the scalar inside. C1, C2, A is A, M by N. Now, you treat C1, C2 as a constant. Say C, say take common out. C times of A is A. M by N. Okay. Take C1, C2 as a common. This is one in C1, C2 times of A. That's all. Last property. Last property. C1 plus C2 times of A. So in every problem, same axioms, but you carefully write down the answer. C1 plus C2 times of A is a M by N. So by using scalar property, send the scalar inside the each entry or multiply with each entry. C1 plus C2. Multiply each entry with scalar Now inside, observe that we have two scalars. So which is written as C1 A is a plus C2 A is a M by N. So once again, matrix addition property, it is written as C1 A is a M by N plus sum of the two matrices. C2 A is a M by N. Once again, take C as a common. C1 is a common from the first matrix. Common procedure. C2 from the second matrix. M by N. So M by N. Right. So this value nothing but C1 times of A, C2 times of A. Hence the result. This is the process to show that given set is a vector space. Hence, finally you write down therefore or hence V is a vector space. Vector space over field F. This is the process to show that a given set with respect to the operations or two operations, vector addition, scalar multiplication, is a vector space. Now I finished two problems. Other three problems are there. You try yourself. If you have any confusion or any problem, ask me. Now other three problems are: let F be the field and S be a non-empty set. V be the set of all functions from S into V. V is a taken as a set of functions whose domain is S, codomain is field. Here operations are already defined using these two operations so that V is a vector space. Similarly, in the fourth problem also, V is a vector space over F with the respect to the following operation. Here, V is considered a set of polynomials. In the first one, functions. Third problem. In the fourth problem, we consider polynomials. Polynomials of degree, any degree, first degree, second degree, third degree. Here they do not mention polynomials only. Polynomials over F. Polynomials over F. If over F means field, A0 plus A1x, A0 only, A0 plus A1x plus A2x square, second order, all possible orders over F. Okay, over F. Last problem, C is a vector space, just like a component, because complex number have two parts, real part, imaginary part, over the real field. Real number into complex number equal to real complex number, because real number, complex number has two part. Each part is a real number. So you solve other three problems in the same manner. This is the first topic of the module 2. Now, at this point, I am going to stop. It's enough for this topic.